Hi, I'm Rhett Jesse, and today we're going to talk about the Metrix digital proximity system, specifically the MX2034 speed transmitter. Now we can configure the MX2034 for vibration or position. Today we're going to use speed. What we're doing today, as far as pulse height adjustment, we could do the same thing with an MX2033 driver. But today we're using the transmitter. What I have is I have the transmitter connected to my computer. It's connected via a USB connection. Now usually there's a cover on this and the DIN rail mounting, so you never see that. But now I have that removed and we're connected to the computer. I also have a speed wheel over to my left. This speed wheel, I can increase the speed from approximately 0 to 10,000 RPM, but I'm only going to go to about 5,000 RPM today. Now on the outside of this wheel, I have 40 holes drilled. Now each one of these holes are 5 millimeters in diameter. The probe tip is 8 millimeters in diameter. So typically you'd want to have the hole as big as the probe itself, but it's not, it's smaller. So we don't have a very good pulse going into our speed measurement system. And I'm going to show you what you can do about that. So I'm going to go ahead and start this machine up. We'll find out what speed it is using our handheld laser tachometer, and it's going to be being reflected off a piece of tape that we have on our wheel. As that piece of tape goes by, we'll be able to pick up the speed with this. So we'll have two sources of finding speed, and they should agree. Okay, so let's go ahead and start up the machine. Let me put on my glasses for that. Let me go ahead and start it up, and we're going to have it come to some low speed, and we're going to see if everything matches. Then we'll go up to higher speed just to show you how the system works. All right, we're going to do some data capture as well, and we'll go ahead and take some data right here. We're at 6.01 milliamps, and speed-wise, we're at 1,258 RPM. So let's go ahead and figure out what we've got. I'm going to go ahead and just stop data capture, and I'm going to look at 10 waveforms just to get some precision. 2, 3, 4, 5, 6, 7, 8, 9. This would be 9. I'll go the other way to get 10. Go over here. And this is just to get more precision on our measurement. Now this is the time period. So the time period I have here is 11 milliseconds. You have to divide that by 10 to get the actual individual waveform of the pulses. So it would be 1.19 milliseconds. All right, or I can take this 84 hertz that we're measuring and multiply it by 10, and that's what I'm going to do. So let's go ahead and do that. So I have 840.27 hertz. All right, so I'm going to multiply that by 60 times 60 to give us how many pulses per minute we've got. So that's about 50,416 pulses per minute via the oscilloscope. So I'm going to divide that by 400,000. That's the scale factor of our, that's how many pulses per minute are going into our MX2034, because it's 100,000 RPM at 4 pulses per revolution. I'll divide it by 400,000. That gets 0.126 times 16 milliamps is 2.016 plus 4 gives us 6.02 milliamps, and we're showing 6.03. It's really kind of spot on with regard to where we should be. So it's working exactly like it should. Now let's go up in speed. Let's go to about 12 milliamps, which is about 5,000 RPM, and to see if we get similar numbers. Let's just do that again, just showing you the accuracy of the system. But before I do that, instead of using a pulse height of just 3.07 volts, I want to double the pulse height. Let's do that with the digital proximity system software. We'll go ahead and go to advanced settings, and we're going to use this speed pulse adjustment slider. We can basically change the scale factor inside the MX2034 so we get a better pulse. Now you wouldn't do this for position or vibration, but you can do it for speed because we're just trying to get a good pulse out of it. Right now we have about a 3 volt pulse. So let's go ahead and use our speed pulse height adjustment tool. And let's go ahead and get and see what the peak-to-peak voltage is measured by the tool. It's 3.13 volts peak-to-peak. What I'm going to do is I'm going to change the slider. We're going to go ahead and move it to the left to see if the voltage increases. If it doesn't, I'll move it to the right. So sometimes it's a little bit of a trial and error process. So let's go ahead and move it to the left. And we'll let it go ahead and do its computations. It's basically changing the scale factor. After it's done, you can say OK and say get peak again. And we can see it went up to 4.82, 4.83 volts peak to peak. And so what I'll do is I'll increase it some more, get it to about 7 or 8 volts. Okay, the change is complete. So you get 7.22 volts, that's plenty. You know, in other words, what we've done is we've changed the scale factor to get more voltage out of our pulse. And for this small target that we're looking at, that's pretty good. And there's 40 on the wheel going all the way around. So that's actually pretty good. So we're going to go ahead and stick with that. If we go over to the oscilloscope, we'll go ahead and say run. And we see now we have a larger amplitude pulse. In fact, we'll stop running. We'll go ahead and look at that. A lot better pulse height. You know, closer 6.2, and I could pick other ones and get closer to 7. But the point is we've changed the pulse height, we've doubled it. And that makes it a very effective pulse to monitor. Let's go ahead and increase the speed from where we're at right now. 1,267, right around there. Let's increase it up to 5,000. So that would just be right around 12 milliamps, so we'll go right to 12. We have 4,923 RPM with using the laser. Let's just see what our speed is using the oscilloscope. We'll stop and we'll get 10 waveforms. All right, we have 325 hertz, and we have to multiply that by 10 to get the true frequency. We're just trying to get better resolution. 3,255.21 hertz times 60. This will give me how many pulses per minute we have is 195,000. We'll divide this by 400,000 equals 0.488 times 16 plus 4 is 11.81. It's pretty close to 11.97. It's very accurate, which is really pretty good. So, in summary, we were able to change the pulse height. We were able to get accurate readings at a lower speed and a high speed, and showed that it works very well. I'm not going to take it up to 400,000 just because this controller is not as stable as I'd like it to be, but otherwise it works very well. Thank you very much.